Okay, guys, so we are ready to roll today. First question is, were you comfortable with the homework assignment out of 5-6? Did it make sense? The substitution problem.
I didn't do 5-6.
Oh, at least you're honest.
I would confess. I didn't do that. I'm sorry.
What, you didn't do all 91 problems?
Many other things to accomplish.
Yeah. You'll notice I have 5-7 posted online, and I have 6-1 ready to post online too. I've been getting ahead. It's been fun. It's like, yes, this is cool stuff. Not as much.
Did you start
cutting back on that a little bit lately, and it's not a time that I should be cutting back, but yeah. I'm taking calculus more seriously. So what I want to ask today, are we ready at the beginning of class to move on, or would you like to look at a couple more hard substitution problems?
Sure.
Okay. I do want to move on to this today, though, as well. So this is section 5-6. Our homework assignment was 1 through 91. So let's look at, let's say, what should be the hardest problems. Usually the last even problem in any section is the hardest. So the first section of problems ended at number 22. I'll look at that one. So 5.6, number 22. We may have to talk about these and work them out together because I have not worked the even problems up front. I don't think we'll run into any trouble. We'll see. If we have the integral of the inverse tangent of x, quantity squared, that's with respect to x, and then that's over x squared plus 1. Okay, guys, now they told us that u is equal to inverse tangent of x. Hopefully you're saying, we don't need them to tell us that. We knew that in this problem. Because we say, let u be whatever's inside of a function. We see that this is inside of an x squared function. And then the nice thing, if we let u equal inverse tangent of x, hopefully you remember your Calc 1, the derivative of inverse tangent is 1 over 1 plus x squared dx, which is what I have here. So I can say du is equal to 1 over x squared plus 1 with respect to x. So this works beautifully, and I can say this is going to be the integral of, I know this 1 over x squared plus 1 dx is all du. The only other thing in there is the inverse tangent function squared, so that becomes u squared du. That's what we do. So we say the integral of u squared, I can't stop myself. The integral of u squared is u cubed over 3 plus c. So we can say, now substituting back in for u, this is the inverse tangent function cubed over 3 plus c. Final answer. That one was not as fun as I thought it would be. Looking at the set of problems 27 through 72, let's look at number 66. Looks fun. It's the integral of secant squared theta. And if you happen to see one in here that you think looks more fun than the ones I'm choosing, please let me know. We'll work any of them in there. I want you to be confident that if you look at any problem in the book, yeah, we know how to do that. There shouldn't be anything in here that we don't feel confidence in working. In this one, it doesn't tell us what to let u equal, nor should it. Is the choice for u obvious in this case? You say, well, from Calc 1, I remember derivative of tangent is secant squared. So if I let u equal tangent theta, du is secant squared theta d theta, beautiful. So that's what I'll do. So now in going in here, and I think last class I might have mistakenly called this trigonometric substitution. This is substitution, integration by substitution that happens to involve trigonometry. It is not trigonometric substitution, which is more fun and harder than this. So we're going to get to that very, very soon. Whenever I integrate this function, I see everything that I'm going to underline is du. Okay? Everything else, well, that's going to be e to the u du. The integral of any exponential function is that exponential function divided by the derivative of its exponent. Derivative of the exponent in this case is 1. So we just get e to the u plus c. Final answer, e to the tangent theta plus c. You see? 72. Perhaps, oh, I like 72. I like it. I recall working a problem similar to that. It's the cotangent of x. I think I might have pulled this problem out from my other examples, maybe, because I looked at it and liked it so much. Natural log of sine of x. So we may have worked this problem because it looks familiar, and it's a wonderful problem. So whenever you're looking at this one, you'd say, well, okay, there's no way I would let this be u, because derivative of cotangent is going to be negative cosecant squared. That's nothing over here from that. But I know derivative of sine is going to be cosine. And the cosine is there because this is understood to be cosine over sine. So I can say, okay, I can work with that, I think. And I'll say, let u equal the sine of x. So du, derivative of sine, is cosine x with respect to x. And then I can say, well, this integral could have been written as cosine x over sine x, natural log of sine x dx. Now, I know that I'm going to cross everything out that's going to be replaced by du. Cosine x dx, cosine x dx is going to be gone. But I'm still going to have that 1 over sine x. Well, sine of x is u. So I'll say, well, okay, this is going to be the integral 1 over u, natural log of u du. Okay. And this is the point where you say, well, how do I integrate the natural log of u over u with respect to u? And if you want to stop it, at this point, I would look at it and say, well, I could do another substitution. This isn't the only way, but it's a way. And so the double substitution, I'll say, let's let w. I'm going to let w equal the natural log of u. Why would I do that? Because in my head, I'm already thinking, well, the derivative of the natural log of u with respect to u is going to be 1 over u. That's nice. I have a 1 over u in the problem. So I'll let w equal the natural log of u, and then dw is going to be the 1 over u with respect to u. So now I know all of this becomes dw, and I'll have, this is the integral of natural log of u is w, so I have the integral of w dw, which now we can finally integrate pretty easily and say that this is w squared over 2 plus c. And then if you say, well, what do we do from there? Back substitute. So you say, well, w was equal to the natural log of u, so this is going to be the natural log of u quantity squared over 2 plus c. And then back substitute one more time. U is equal to the sine of x, so our final answer is the natural log of the sine of x, all of that quantity squared over 2 plus c. I would say that problem increased the fun factor. I would. In the definite interval part, problems 79 through 90. If you want to look through some of those, let's see, we'll look at one algebraic and then one trigonometric. So 86 and 90, for example. In looking at number 86 in 5-6, we have the integral from 10 to 17. And then on the inside of our integral, it's the rather innocent-looking function x minus 9 to the negative 2/3 power dx. This is not a problem in which we would actually be required to use substitution. The reason I'm going to is that's the point of this section. So I'll say, well, okay, I'm going to use substitution and the change of variables formula like they suggest. So I'll say, okay, let u equal what's inside the function. So u is equal to x minus 9. U equals x minus 9. Du is simply dx. And then you'd say, well, if you're going to change your variables, I can't say my limits of integration are from 10 to 17 anymore, because please remember, this is with respect to x. So you could literally say this means x equals 10 to x equals 17. I can't keep my limits in terms of x when now my problem is in terms of u. So I would say, well, what is u is a function of x, u solved in terms of x, so what is u of 10? U of 10 is simply 10 minus 9, 1. U of 17 is simply 17 minus 9 for 8. So we'll say this becomes the integral, instead of 10 to 17, 1 to 8, and instead of the group x minus 9 to the negative 2/3, we just have u to the negative 2/3 du, since dx is du. Now we integrate, we know we add 1 to the exponent. U to the negative 2/3 plus 3/3 is u to the 1/3. Divide by that new exponent. If you divide by 1/3, you're multiplying by 3. So I'd say 3u to the 1/3 evaluated from 1 to 8. That works great, because we can see when we plug in the 8, it's the cube root of 8, which is 2. 3 times 2 is 6. When you plug in the 1, I'm just saying cube root of 1 is 1. 1 to the first, still 1. Times 3 is 3. So 6 minus 3, 3 is what it would be.
Do you have to use U-substitution on that problem?
So to answer that question, no. But why did I? Because the section told me to. But you're right. As soon as I saw this, you could just say, well, this is the group x minus 9 to the 1/3 times 3, just by looking at it, and then evaluate from 10 to 17. So substitution is not required on this problem, but I would say within this section it was, because the point of this section was substitution. Yeah, Clint, I would say what they needed to do is put a harder problem than that, because substitution's not needed on that. If they wanted us to have to use substitution, they should have made us use it. Number 90. Let's see if they make up for it on this one. It is wonderful trig, so that's a good thing. Pi over 3 to pi over 2. And it gives us cotangent squared of x over 2. And then cosecant squared x over 2 dx. Okay. So we always say we let U equal what's inside of a group. I actually have quite a few groups. One U-substitution that would not be enough, because you just have to do another U-substitution later. One trivial one you could do is say, well, let U equal x over 2. But I guarantee you, you're not going to be much better off because you still have cotangent squared U, cosecant squared U du, and you'd have a factor of 1/2 out in front. Not going to help a whole lot. So I'm going to go ahead and say, well, I know each of these are inside of a function. This is the cotangent group squared, the cosecant group squared. When I think derivative of cotangent, negative cosecant squared, the derivative of cosecant is negative cosecant cotangent. Actually, either of those would work in this case. I think the easier one is going to be if I let U equal this one. But even if I let U equal this, the derivative is still there. But the problem is that that first term, you're only going to get rid of one of the powers of it. You're still going to have a cotangent floating around if you let U be this. That wouldn't be the end of the world. We could get rid of it, but this will be the easier method. And we're all about doing it the easier way. So we say, okay, let U equal the cotangent of x over 2. Now, we remember, okay, derivative of tangent, secant squared, derivative of cotangent, negative cosecant squared. So I'll say du is equal to negative cosecant of that angle squared. Am I done? Times the derivative of the angle. Well, you can think of that angle as 1/2 x. So the derivative of the angle is 1/2. And then, can't forget our dx. Okay. So now I know that I need to see everything in there. I already see most everything in there. What I don't see is a negative 1/2 times the dx. So what I'll do is I'll go ahead, instead of rewriting the problem, I'm just going to go up to the original and say, I need a negative 1/2 on the inside. If I multiply the inside by negative 1/2, I better multiply the outside by negative 2 to make up for that. Okay, so now the problem is just as it was. In this same step, though, I'm wanting to do a U-substitution. In order to do that, I also need to change my limits of integration. So I'll say, well, what would U be if I evaluated it when x is pi over 3? Cotangent of pi over 3 divided by 2. That's going to give me cotangent of pi over 6. And guys, this is where, if you haven't memorized your unit circle, please do so. It makes things so much easier. So I'd say, well, if I'm at pi over 6 on the unit circle, what I'm supposed to know is that means the x value on the unit circle at that point is the square root of 3 over 2. The y value, the sine, 1/2. So I could say, well, I know cotangent is cosine over sine. So the cotangent of pi over 6 is the square root of 3 over 2 over 1/2. So I'd say, well, this is square root of 3 over 2 over 1/2. When I divide by 1/2, I'm multiplying by 2. The cotangent of pi over 6 is just the root of 3. Okay. Now, what I would say in a problem like this is the exact answers only to avoid someone just saying, well, I can type that into my calculator. No, that would be cheap. I want you to get an exact answer. Nice. So now we'd say U evaluated at pi over 2 is just the cotangent of pi over 2, cotangent pi over 4. We should know that pi over 4 is the point on the unit circle, and anything over 4, your sine and cosine are always the same absolute value. So it's always going to be 1 or negative 1. At pi over 4, it's 1 because we know both the x value and y value component. The x value is going over less, the y value is going up more. Square root of 2 over 2 for both. So I can say the cotangent, cosine over sine, 1. That means, now that I have this set up, this problem changes to -2 times the integral. The lower limit of integration is the square root of 3. The upper limit of integration is 1. So we're actually going backwards now from square root of 3 to 1 because placing it into our formula gave us this direction. Cotangent squared x over 2, we know that becomes u squared. Everything else here, -1/2 cosecant squared x over 2 dx, all of that is du. So every bit of this gets replaced with a du. So now the integration is pretty easy. And we say this is going to be -2 times the root, u cubed over 3, evaluated from the root of 3 to 1. So I'll say, well, okay, it's going to be -2 times. When I evaluate this at 1, I get a 1/3. When I evaluate it at the root of 3, the root of 3 cubed, I know the root of 3 times the root of 3 is 1 over the square root of 1 minus x squared. The integral of that, the definition, is the inverse sine of x. So I can say, okay, it's the inverse sine of x evaluated from -1/2 to the square root of 3 over 2. And now what I want to help you recall is that whenever you're talking about any inverse trig function, the answer is an angle. So if it says inverse sine, inverse cosine, inverse tangent, you know the answer you're looking for is the angle theta. So I can say, when I'm looking at this, the inverse sine of the square root of 3 over 2, that's asking me, when is the sine function the square root of 3 over 2? And I can say, well, that's true at an angle of pi over 3. At pi over 3, I know my cosine is 1/2. My sine is the square root of 3 over 2. So I can say, this is going to give me the inverse sine of the square root of 3 over 2 minus the inverse sine of 1/2. I already know the inverse sine of the square root of 3 over 2. That's at pi over 3, or 60 degrees if you prefer degrees. I definitely prefer radians. So I'll say pi over 3 radians is when the sine function is square root of 3 over 2. When is the sine function 1/2? The sine function is 1/2 at pi over 6. We know the cosine is the square root of 3 over 2, and the sine is 1/2. Inverse sine of 1/2 going to be pi over 6.
Yeah.
Say that again, please.
Negative.
Oh, well, it is, isn't it? Good catch. So, hey, that's just minus a negative pi over 6. Because it's a reference angle with pi over 6, so I'll say, instead it's down here. Thank you. And we remember that the sine function has to be restricted from negative pi over 2 to pi over 2 in order for the inverse sine to exist. So if someone had said, why didn't you say the answer was 11 pi over 6? That's a coterminal angle to the correct answer, but the inverse sine function is only going to exist from negative pi over 2 to pi over 2, so you can't say anything outside of those angles. Notice the sine takes on all of its negative values in quadrant 4, all of its positive values in quadrant 1. So I can say it's a negative pi over 6, pi over 3 plus pi over 6, pi over 2. That's more of a trig question than it is a calculus question. Okay. A more fun problem. If I give you, let's say, the integral of dx over x on the square root of x squared minus 4. And then we'll say this is evaluated from 4 over the root of 3 up to 4 over the root of 2. Okay, now what I don't have here, and I would have to put on some test or something for you, is that the integral of 1 over x on the square root of x squared minus 1 dx, that is our inverse secant function. This is not one of them I expect you to memorize, but if I give it to you, if I give you this base formula, we should be able to work things like this out. Now, the problem in this one is that you see, well, I don't have x squared minus 1 in there. I need an x squared minus 1. So I need to force what's on the inside to be that. So I'll say, okay, the only way I could get this to be some constant squared minus 1 is if I force this leading coefficient to have a 4. And that seems very hard. And this is one of the things, I think the way I do it, and you can look at the book, and so when I'm looking at this and I'm thinking, I need this, I think, what's the easiest way for this to be that? I'd like it to have a 4 coefficient here. So here's what I'm going to do. I'm going to say, I need to have a 4, I'm going to call it u squared minus 4. If you think, why do you need a 4u squared minus 4 in there? What I'm thinking of is because I would be able to factor a 4 out of that and call it u squared minus 1. That's the whole point. I'm wanting to get to that. Okay? So I think, well, the only way I could get to it is if I could factor out a 4. Here's what I do now. So if 4u squared minus 4 is what I need in there, I'll let 4u squared equal x squared. So you just say, instead of x squared, I wish that was a 4u squared. So we're going to substitute and make it that way. So I'll say, okay, then if I solve for u, I know u squared is equal to 1/4 x squared, which would make u equal to 1/2 x. Furthermore, du is 1/2 dx. Okay, my limits of integration. I'll go ahead and change them in the same step. So I'll say u evaluated at 4 over the root of 3 is going to be 4 over the root of 3 times 1/2. So it gives me 2 over the root of 3. U evaluated at 4 over the root of 2, 1/2 times that, which gives me 2 over the root of 2. Okay, so I want to see if there's some progress now. Before I can just force this in there, though, I've got to be able to see everything here over here. So I already know that in the place of the x squared, I'll be putting a 4u squared. That's going to be fine. In order to make that substitution, though, du has to be 1/2 dx. I need to see a 1/2 dx in there. So, as always, I'll force a factor of 1/2 on the inside, which means on the outside I need to multiply by 2. And I think this problem's pretty much ready to work now. I'll say this is 2 on the integral. No longer 4 over the root of 3, but 2 over the root of 3. 3, John. Up to 2 over the root of 2. On the inside, 1/2 dx becomes du. This square root, the whole point, what I wanted to do was to rewrite this as, remember, x squared is 4u squared. I will now be able to factor the 4 out of that group and have the square root of u squared minus 1 in there, which is what I want. On the outside, though, this x, I don't want to leave it an x. We say that it needs to be in terms of u. So if I have u is equal to 1/2 x, it's pretty easy to solve for x. X is equal to 2u. So I'll say on the outside, I already have a 2u. Okay. So in this next step, here's what I'm going to do. Have my integral from 2 over the root of 3 up to 2 over the root of 2. We know that there's a common factor of 4 in here that's going to come out. What I'm going to be left with in that square root is just the square root of u squared minus 1 after I factor out that square root of 4. So it's the square root of 4 that comes out. Square root of 4 is 2. I already had a 2 down there, so that's a 4u out in front. Now notice, my formula here doesn't have a constant in the denominator. I don't want a constant in the denominator either. So I know that this would make a factor of 2. I already had a factor of 2. So that's a factor of 4 in the denominator that I can and should factor out. So that's going to give me a 2 over 4 in front. It changes the coefficient of this integral from 2 to a 1/2. That's one of those steps that when I show my work on paper or the book tries to show its work, that a lot of people go, whoa, he made a mistake from here to here. No, it's just trying to factor terms out, and that's what happened out in front. Now, this 2's already been taken care of, along with the square root of 4 out in front. So I have u on the square root of u squared minus 1. Numerator still du. Everything's workable now. That fits exactly the definition for the inverse secant. So I can say, okay, my answer is going to be 1/2 the inverse secant of u, and I don't say plus c because I know it's going to be evaluated from 2 over the root of 3 up to 2 over the root of 2. We say, okay, this is going to be 1/2 the inverse secant of 2 over the root of 2 minus the inverse secant of 2 over the root of 3. Now, hopefully you remember the trick in evaluating any of the inverse cotangent, inverse cosecant, inverse secant. You simply say, I don't want to think about what the inverse secant of 2 over the root of 2 is. I know that the secant function is nothing more than the reciprocal of cosine. So the inverse secant of 2 over the root of 2 is going to be the inverse cosine of the reciprocal of that angle, the square root of 2 over 2. That's something we can handle pretty easily. Minus the inverse cosine of the square root of 3 over 2, like that. So now my final answer, and I ran out of room down here, so I'll finish it up at the top. This is going to equal 1/2 times inverse cosine square root of 2 over 2. That's pi over 4. Halfway through the first quadrant. Inverse cosine of square root of 3 over 2, pi over 6. We know pi over 4 minus pi over 6. That's like 3 pi over 12 minus 2 pi over 12, so it's pi over 12. 1/2 times pi over 12. Pi over 24. So again, that problem's almost as tough working with a trig as it is, I don't know, the calc part's kind of fun too. That's just a good problem. And just think, that's number 3, and my problems are supposed to be in increasing order of difficulty. I have 17. So, I shouldn't say things like that. The next one here, guys. Oh, see if you can make a connection with what I did in that problem with what we're going to need to do here. And I hope the connection should be obvious. That's my goal. The more problems like this you work, the more comfortable you're supposed to get into saying, oh, okay, that's what you do. So, what does this integral look like?
The inverse tangent.
Yeah, it almost looks like the inverse tangent. You say, but if it were the inverse tangent all alone, it'd just be x squared plus 1. We don't see an x squared plus 1. We need to see an x squared plus 1. So I'd say the only way I could get this denominator to be x squared plus 1 or 1 plus x squared is I could say, well, what if that x squared had a coefficient of 4? Then I could factor a 4 out of that group and I'd have a 1 plus x squared. So I can say, well, instead of just saying what if, let's force it to happen. So I'd like to have a 4x squared there. So I'll just say, I'm going to say let 4x squared equal u squared. So I'll say, well, okay, if that's what I want, and I can say, well, okay, oh, and I'm sorry, I want to have a 4 there. So this is actually backwards, I apologize. I want u squared to equal 4x squared. So I'll say, well then, u is just going to be 2x, the square root of both sides, and du 2dx. So I can say, well, okay, if this enables me to have that in there, then I'll say u squared is 4x squared, u is 2x, du is 2dx. And I can say, well, okay, so if I put this 4x squared and then replace it with a u in there, and oh, I undid it. I was doing it right to begin with, now I'm not. This is okay. I want to make sure you say, well, okay, why did he catch himself? This is the thing, as you're working problems, you need to be able to see, I need to stop and go back and think about this. Notice what I've done here, guys. Nothing wrong with a substitution. It's just not a helpful substitution. Because if I tried to go back into the problem and do this, and I'd say, well, okay, could I force this in there? I could, but I don't want to. Because this would give me, if I say u is 4x squared, when I try to substitute that in there, I have a 1x squared. So this would be plus 1/4 u squared. You're like, gee, John, you really helped out that problem. No, I made it worse. Do you see what I'm saying here? So I'd say, I want the 4u squared, not a 1/4 u squared. I have an x squared, so I'll say, okay, back to the drawing board. Maybe I did that on purpose. No. I want a 4u squared in there. So I'm thinking, I want to replace x squared with a 4u squared so I can factor a 4 out of the denominator. Now this is the right track. So I'll say, okay, if that's the case, u squared 1/4 x squared, u is equal to 1/2 x. du, just like our last problem, 1/2 dx. Identical to the last problem, other than it being an inverse tangent function. So I'll say, okay, I need to force a factor of 1/2 in there. I'll do it. Multiply by 2 on the outside. Now I'll say, okay, this is 2 times the integral. The entire numerator is replaced with a du. The denominator, 4 plus x squared, replaced with 4 plus 4u, because 4u squared is x squared. Now I can say, okay, all I have to do is factor a 4 out of the out of the denominator. That 4 gets pulled in front, becomes 2/4. So I'll say 1/2 the integral du over 1 plus u squared. Now this is just your inverse tangent function directly. So you could say your answer is going to be 1/2 the inverse tangent of u plus c. Okay. Then you can say, well, you want your final answer to be in terms of x. We know u is 1/2 x, so my final answer, final answer, 1/2 inverse tangent of 1/2 x, or I think I'd prefer to say x over 2, plus the constant of integration. So the key to these problems is to visualize in your mind what would help in that denominator. When we looked at this and you said, okay, it looks like an inverse tangent function, but an inverse tangent function is 1 plus x squared. So I'm thinking, well, it would help if I would have 4 times some variable squared there, so I could factor out the 4 and have it look like this. So automatically, I was going in reverse to begin with. I said, well, let 4x squared equal u squared. That didn't help, but it did help to say, well, instead of that x squared there, what do I want to replace it with? I want to replace it with a 4u squared, which will enable me to factor out that 4. Now, another one. What if we have the integral, the natural log of the inverse cosine, all of that with respect to x. We're dividing that by an inverse cosine of x on the square root of 1 minus x squared. All sorts of stuff going on in this one. If I said, let's try a U-substitution again, that U-substitution, you could do it in 1 step, you could do it in 2 steps. If you did it in 2 steps, you would say, well, let's let u be what's inside the natural log function. You say, okay, if u is inverse cosine of x, then du is -1 over the square root of 1 minus x squared. We see that in there. That would be adequate. You could get rid of it in 1 step, though. Instead of saying let u equals what's inside the natural log function, and you'll see this as you get more and more used to using substitution, what if I let u equal the natural log of the inverse cosine of x? Then we think, okay, the derivative of that, what's the derivative of every single logarithmic function in existence? 1 over what's inside the function times the derivative of what's inside the function. So I can say times the derivative of inverse cosine of x, which is our -1 over the square root of 1 minus x squared, and all of this is with respect to x. So I can say, well, that du, every single bit of that, with the exception of the factor of -1. So I'll say, well, I need to multiply by -1, and I'll make up for it by multiplying by -1 on the outside. So I'll say, okay, this is the negative of the integral. And I can say, well, everything that I'm going to circle up here is going to cancel out. The inverse cosine, square root of 1 minus x squared, all cancels out. The -1 dx cancels out. So the only thing I'm left with is the natural log of the inverse cosine. And every bit of that is just u. So this problem works so well now. It's just u to u. You turn this beautiful problem to a simplistic problem by 1 substitution. So this is going to give us the negative of the group u squared over 2 plus c. Have to put the plus c since it's an indefinite integral. And now our final answer, we know that u squared, u is representing the natural log of the inverse cosine. So we'll get the natural log of the inverse cosine function all of that squared, and then I'll make it negative out in front. All of that divided by 2 plus c. So that was a problem that, in the beginning, I would expect most people to think that that problem looked fairly intimidating. But by wisely choosing your substitution, it made it not too bad. Now, another option would have been let u just equal the inverse cosine. But the problem with that is you would have had to do another, it would have been a double substitution problem. You would have had to let u equal the natural log, w equal the natural log of u to finish it out. Okay. Exponential function. When I'm looking at this one, again, thinking, okay, the problems in this section are also going to use substitution. And I see I have the exponential function 10 to the x squared. I can integrate an exponential function if it's just 10 to some linear power, but not a squared power like that. So what I'll do is let u equal x squared. So du is 2x dx. And then I can say, well, okay, if du is 2x dx, I need to see a 2x dx in there. So I already have an x dx, multiply by 2 to get the 2x dx. If I multiply by 2 on the inside, I multiply the outside by 1/2. So now, when I look at this, and I have my 2 on the inside, I know all of this is going to become du. I'll say this is going to equal, I almost kept my units of, or sorry, my limits of integration. That would have been bad. So in this same step, I want to evaluate this function. I can say, this is going to make it so ridiculously easy. Notice now. I almost don't want to do that. Because that takes the fun out of it. U evaluated at -2 is just going to be -2 squared, 4. U evaluated at 2 is 2 squared, again 4. So we're integrating this function from 4 to 4. Ooh. So if you think, why is that the case? 10 to the x squared is an even function. X is an odd function. Odd times an even is an odd. This function is odd, which means f of x is equal to the negative of f of negative x. So I can say it's symmetric with respect to the origin. So if I go off 2 units to the left, 2 units to the right, they're just going to counteract one another. The area underneath the x-axis is equivalent to the area above the x-axis. But we still want to integrate for the fun of it. And then we know the answer is going to be 0, which isn't fun, I understand. In this problem, I'll say, well, okay, I have the 10 to the u, and everything else is du. So I would say, well, the integral of 10 to the u du, I'll put my 1/2 out in front. Integral of any exponential function is that exponential function divided by the natural log of its base. Sorry to say natural log of u, natural log of 10. And then you would evaluate this from 4 to 4. Ooh. Don't like that problem. Okay. This one's tougher. That's tough. If I said, what would you do on this problem? What would you think, guys, at first glance?
Double substitution.
Solution? No. What I would think you might try is you say, well, in the techniques of the last section, you let U be whatever's inside of a group to a power. I wouldn't write this down. This will not work, but this is the kind of thing you've got to think why it doesn't work. And I have to go through the same process. The first thing I might try on a problem like this is, what if I let U equal 5 to the 2x minus 1? That would fail miserably. Because the derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base with respect to x. Now, I see the dx in there, and I can multiply by 2 natural log of 5 if I divide by that out in front. But do I see a factor of 5 to the 2x in there that I could just replace in there? No. You can't multiply by a variable to get rid of it and call it du. You can't do it. Constants, no problem. So if my derivative was just that, not an issue at all, I could work with it. That is what caused the problem. So I can say, okay, if that doesn't work, what does? So here's what I'm thinking. I'm thinking it's an inverse trig function. And the inverse trig function is going to be 1 minus a variable squared. So here's what I'm going to try to do. I'll say, if I rewrite this problem, admittedly, this is a tough one, but that's okay. I want to rearrange this, and let's say I gave you a hint, and I said that the answer to this involved an inverse sine function. So that would be my big hint in this problem. You say, oh, the answer involves an inverse sine. Wow, okay. So that means I need a 1 minus some variable squared here. Okay, so if this needs to be a 1, then I'll say, okay, what I'm going to try to do here is factor out a 5 to the 2x power out of this group. So think of that, guys. If I have 5 to the 2x minus 1, and I'm asking you, I want you to force a factor of 5 to the 2x out of that. You'd say, well, okay, 5 to the 2x, 1 minus 1 divided by 5 to the 2x, which that's the same thing as 5 to the 2x times the group 1 minus 5 to the negative 2x, right? So I could say, if all of that is inside of that square root, what happens when I say I want to bring this term out of the square root? The square root of 5 to the 2x is 5 to the x. Okay? You just say power to power. It's like saying to the 1/2 power, 2x times 1/2 is x. So I'm going to say this is 5 to the x on the outside. And on the inside, it's going to be 1 minus 5 to the negative 2x. Be my first step. And then I'll say, notice 1 minus u squared form in denominator. That's automatically an indication, hey, this is going to be an inverse sine function. Go ahead.
What happened to the 2 when you took it out, the 5 to the 2?
What happened to
the 5 to the 2x?
Oh,
You took it out.
so I factored, so imagine all of this is inside, well, you don't have to imagine, I'll put it all. So all of this is in a square root. All of this is in a square root. So then the square root of 5 to the 2x is just 5 to the x. And then I still have the square root of that term left. Is that what you were asking, Sawyer?
Thank you.
Okay, all right, sure. Okay, here's my thinking on this problem. If I'm trying to force an inverse sine, I want to see 1 minus u squared in there. Okay, so 1 minus u squared equals what I have, 1 minus 5 to the negative 2x. So clearly, u squared has to equal 5 to the negative 2x. So u has to equal the square root of that, which is 5 to the negative x. So du, say the derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base. So I'll say du is 5 to the negative x times negative 1, the derivative of its exponent, times natural log of 5, the natural log of its base, dx. So I can say this problem can be written in the form 1 minus u squared if I'm able to see this in the problem. So first question, do we see a factor of 5 to the negative x in the problem? Yes. Fantastic, guys. 5 to the x in the denominator is 5 to the negative x. I don't see a negative 1. Well, I'll put it. Remember, constants we can always put in there. Have to multiply the outside by negative 1. Do I see a natural log of 5? Nope. I do now. But if I multiply the inside by the natural log of 5, I need to divide the outside. So I'll improve my outside. My outside is negative 1 over the natural log of 5. So I can say, using this U-substitution, it's going to change my integral to negative 1 over the natural log of 5 on the integral, negative 1 dx, natural log of 5 over 5 to the x. All of that becomes du. So the entire numerator and that term becomes du. This right here becomes the square root of 1 minus u squared. And then I can say, yes, that is by definition the inverse sine function. So I can say my answer is going to be negative 1 over natural log of 5, inverse sine of u, plus c. And then we say, well, okay, your final answer needs to be in terms of x. U is equal to 5 to the negative x power. So I'll say, okay, final answer, negative 1 over natural log of 5, inverse sine. I think I'd prefer to call that 1 over 5 to the x for the final answer, plus c. Is that one okay? Yeah.
But for ones like that, you're going to hint to us if it's the negative inverse.
I think I would have to. I think I would have to. I would feel cruel just giving you that and saying, good luck. That'd be cruel.
I just write notes.
No. He never said fun about that.
No, it's very fun. I bet you other classes don't even attempt problems like that. That's a rough problem. But it's one of those. It's kind of fun yet frustrating because once you see what to do, the doing it is actually not bad. Which is the problem with Calc 2. You get to a problem and you're like, I don't know where in the world to start. If somebody gives you that initial push, you're like, oh, okay, then it's just downhill from there. But seeing that initial step is the roadblock oftentimes. And the thing I can say, the best thing to get over that is to work problems, problems, problems. Which is why in class you see me work so many problems. My true philosophy and how to get this into your mind is just seeing as many different examples from easy to hard as you possibly can.
You said you got 17 on these?
think 10 of them can
So
work.
what happened to that?
I think like 10 of them.
So that
Aren't
was
we
7.
supposed to, aren't we supposed to have like a 10-minute break each class?
Yeah, what
So
happened?
it's like class number 5.
Don't you want to get out at 3:50?
Yeah, we get out 3:50.
No, there's already
3:45?
like 2 or 3 of them, so you owe
Can
us
I-
like 20, 30
can I ask you
minutes.
something?
I talked it today.
Y'all are wasting my time now.
Yeah.
This rack, like every day we don't get 10 minutes to rack.
No. It just means, see, you get those back on test days when I don't limit your amount of time or allow you to take it in the testing center. A lot of teachers told you from the time class begins to the time class ends. I don't care if you stay till 11 o'clock at night taking my test.
Really?
Seriously, security always says, oh, it's just John giving his night class a test. I'll give my night classes a test. It starts at 6:15. They'll be here till 11, and security comes in there. I'm like, what are you doing? Oh, it's just Jonathan giving the test. Never mind.
That's when food in the room next Wednesday.
Number 8.
Bring dinner.
Yeah, bring food.
They're long.
Aha.
4 hours on one last year.
Okay, guys. I'm trying to trick you on this one.
Because it looks like tangent.
Exactly. I wanted you to think, ooh, this is an inverse tangent function. And if you think that, you are completely wrong.
Oh,
And I need you to see why. An inverse tangent function, if you look in the definition, it has a constant over x squared plus 1. So something you might just want to put in the back of your mind is that it's only inverse tangent if the degree of the numerator and denominator differ by 2. So now, could it be an inverse tangent function if it's x over x cubed plus 1 or x cubed plus x? It could be. The degree must differ by 2. So in this case, it is not an inverse tangent function. No way, no how. It's just not. So you say, okay, so what is it? This problem could have been from our last section. It's just a simple substitution problem where you say, if I let u equal the denominator, then du is 2x dx. That numerator is twice that. This is going to be 2 times the natural log of u, where u is equal to x squared plus 1. Nice. Let's see. So I'll say, this is going to be, if u is x squared plus 1, so you let u be the denominator, then the derivative of u is 2x dx. I noticed there that I have a 2x dx as a factor in the numerator along with a 4. So I could say, well, that 4 I'm going to call 2 times 2. I know this 2x dx is all going to become du. I'm going to factor this other 2 out in front. So I'll say I'll have 2 times the integral. The numerator 2x dx, all of that becomes du. The denominator, x squared plus 1, just becomes u. So I can say, what is the integral of 1 over u with respect to u? I know that that's the natural log of u. I'll have 2 natural log of u plus c, where this is 2 times the natural log of x squared plus 1. It would be ridiculously redundant to leave the absolute value on this one. Again, if you want to, I'm fine with that. But I would rather just say x squared plus 1. We know x squared plus 1 can only be a positive number anyway, plus c. So it would be redundant and repetitive to put the absolute value. So I said these went in increasing order of difficulty. 8 was a step down, I think, because that one wasn't as fun. Oh, this one is. So I want you to look at this one and tell me what you think is going to be in the answer.
More letters than numbers.
Well, I can't disagree with that. Does this look like one of the forms we started class with?
Inverse sine.
Yes. Anytime you have a constant minus a variable squared under the square root, you think this is an inverse sine problem. The problem, of course, with this is inverse sine is for the square root of 1 minus u squared. So I can say, okay, I need in this problem, here's what I'm going to think of. The only way that I could get this to come out is if I had a, because I need this 9 to become a 1. So I need a 9 minus 9x squared, then that would be easy. I'd get the square root of 9 is 3, and I'd bring out a 3, and I'd say the square root of 1 minus u squared. So instead of that 16x squared, I wish that was a 9u squared. That would make it a lot easier. That's the substitution I made. So I'm saying I wish that 16x squared was a 9u squared. That's the logic I'm using, because I know that that 9 can factor out easily. So I'll say, in order to do this, I'll solve for u now. So I would say, well, divide by 9 on each side. And I'll say u squared is equal to 16 over 9x squared. So u is going to equal 4/3 x. du is going to equal 4/3 dx. So now, and something that I did on some of the problems as I worked online, because bad habits of working things the way I just like doing instead of the way the book does. But you'll notice on some of them, what I did, instead of saying du is 4/3 dx, in the substitution, and this works perfectly fine, you might like it better yourself, instead of forcing a factor of 4/3 in there, you can just say, well, solve for dx here. Dx would equal 3/4 du. In fact, I'm going to work this problem this way, just to show you, you can. So I'm not going to worry about saying, oh, well, I needed a 4/3 dx in there and put in a 4/3 dx. I'm going to replace dx with 3/4 du. And notice that 3/4 can be brought out front anyway, which is the same thing you'd have to do the other way. Doesn't matter either way you'd work it. So I'll say, okay, that numerator, dx gets replaced with a 3/4 du. In the denominator. The whole point of doing this was so that I could say 16x squared is the same thing as 9u squared. So I'll say the square root of 9 minus 9u squared, and I have this du. So my U-substitution is kind of in the way, so I'll bring it over here and say this becomes, I know the 3/4 gets moved to the outside. Do you see I'll have another factor of the square root of 9 in the denominator, which will come out as dividing by 3. So, in fact, I'll just go ahead and show it. I would have 3/4 out front, my du on the inside, and then I have a 3 on the square root of 1 minus u squared. This 3 gets brought out front, divides what's currently there, so I'll get a 1/4 the integral du over the square root of 1 minus u squared. So once again, we use substitution to force what we had into what we needed. This is now an inverse sine, so I can say my answer is 1/4 inverse sine of u plus c. So 1/4 inverse sine. U in this problem, u was 4/3 x, so it's 1/4 inverse sine of 4/3 x, or I could call it 4x over 3 plus c.
Do we have to do it the way you just did, or can we just do it the way we've been doing it?
I don't know what you mean. Oh,
Like
solving for dx? Yeah, you could just done it the way
it just seemed like the other way
yeah,
was a lot easier.
Oh, no. Well, it's whatever you prefer, but it's the same amount of work. If you did it this way, you just said, I need to see a 4/3 dx in there. Okay, I'll put a 4/3 dx. All of that becomes du. In order to put the 4/3 there, you'd have to put a 3/4 out front. Same thing either way. You'll get to that point. Either way you do it. I would say it's 6 of one and a half dozen
I
of
did
the
it like a little bit different, I guess. Like I went ahead and subbed the U in at the bottom, and then just brought the third out, and then only added a 4 in.
Mhm.
So they just combined the bottom and everything.
As long as you get to the final answer, that's all I care about. And as long as you're not using a calculator with a symbolic manipulator that gets to the final answer, that would be annoying. Because
Yes.
it is
You
possible
make those.
you could have just typed the original problem into a calculator and said integrate, and it spit out that answer, and that would suck all the fun out of these problems.
It's like a fun checker.
So let's say hypothetically we were to get one of these. Where would we find it?
I'm not even going to say.
Ask.
Oh, really?
It sounds like you're disappointed.
With this one, yes. But I think we do need to look at it, just to make sure. But another one of those problems, if you do it the right way, it's super easy. If you do it the wrong way, obviously, it's not. As you look at this problem, guys, does something come across to you as, hey, I know what to do? Very first step.
Factor an x.
Take the natural log? No.
There you go. Distribute the denominator into the numerator, and you say, well, e to the 2x divided by e to the x, whenever you divide variables with these are like bases, you just subtract the exponents. 2x minus x, 1x. I can say this is equal to the integral of e to the 1x minus e to the 4x divided by e to the x. Again, when you divide like bases, you subtract exponents. 4x minus x, 3x. And that's why I was going e. Because now it becomes a easy integration problem. You just say, well, the integral of e to the x is e to the x. Minus the second one, the integral of e to the 3x is e to the 3x divided by the derivative of its exponent, 3, plus your constant of integration. And so actually I'm happy with that answer. I started out clean it up, but nope, I'm happy with that.
So if we didn't catch that, how would we go about it?
Wow. If you didn't do it that way, I almost think it's unintegrable. Substitution would not really help in this problem. I think you just have to do it algebraically first. Yeah.
They might have them on tables.
Maybe. I don't know. It'd have to be a pretty extensive table to have that open on. 11 here. It's another e to the x, but I think you'll like this one better.
You were in 2 steps?
No. E to the x times the group e to the 2x plus 1 quantity cubed. Oh, the x. Of course. Now, can I distribute e to the x through that group? No, you can't. Although I've seen a lot of people try that algebra. Yeah, you could, but you're wrong. So right now it's not in a form where I can deal with it. So if I said, hey, let's use substitution on this, the obvious substitution is great. What's inside a group to a power? Okay. So if I let u equal e to the 2x plus 1, then I'd say then du is equal to e to the 2x times the derivative of its exponent times 2 dx. And uh-oh, I see a problem. E to the 2x, well, why am I doing that again? times 2dx. I don't. The problem is I'm repeating myself. But sorry. Now when I look at this, though, guys, this is a serious, legitimate problem that I need you to see. That substitution just failed miserably because I can say, can I see? So could I see a 2dx in there? Well, of course I could. That's not a problem. Can I get a factor of e? So now notice that doesn't count. That's part of the u. This is u to the third. Other than that term that I'm going to substitute, is there any way to get an e to the 2x as a factor in there? That's e to the x. Didn't work. So I say, that idea, good idea, doesn't work. Oftentimes with integration problems, we have to go through this process. That's one of the reasons I love it. So I'll say, okay, try again. So now, where I was saying, what's the obvious U-substitution? And you said exactly what I wanted you to, e to the 2x plus 1. Now we said, okay, that's clearly not the obvious choice. So I said, okay, what if I let u equal e? Nice. U is e to the x. Du is still e to the x dx. Gorgeousness! Because I see that's my e to the x dx. All of that becomes du. So this is the integral. If u is e to the x, what do I replace e to the 2x with? Fantastic. So I could say, I know u squared is e to the x squared, which is e to the 2x. So u squared is e to the 2x. So I said this group becomes u squared plus 1 cubed. All of that's du. Can I integrate that?
No. You gotta use W in there.
No. So why not? So if I tried, W equals u squared plus 1. dW would be 2u du. Is there any way to get a factor of 2u du in there? No. So what we have to do is multiply this out, cube it out, get the polynomial, and integrate the polynomial. And remember, that's very easy. Pascal's triangle tells us that anytime you want to cube something, it's just going to be 1 times the first number cubed plus 3 times the first number squared times the second number plus 3 times the first number and the second number squared plus 1 times the third number cubed. Gorgeousness. So I can say this is equal to the integral of 1u squared, and I'm going to show out my work here. 1 times u squared, it's the first number cubed, plus 3 times the first number squared times the second number, plus 3 times the first number to the first times the second number squared. Alternatively, if you just wanted to multiply this out 3 times, that works too. Plus the 1 times the second number cubed. Pascal's triangle. So I can say, well, u squared cubed, that's u to the 6th. This is the integral u to the 6th plus 3u squared squared, that's 3u to the 4th, plus 3u squared times 1, and then plus 1. So Pascal's triangle made the algebra in this problem not that bad. Integrating this, we know that we get to u to the 7th over 7 plus 3u to the 5th over 5 plus 3u cubed over 3, so that's just plus u cubed, plus u plus c. Final step, you substitute what u is. U is e to the x. So I know u to the 7th would be like e to the 7x. E to the x to the 7th is e to the 7x. So I'll say e to the 7x over 7 plus 3e to the 5x over 5 plus e to the 3x plus e to the x plus c. So the fun thing about that one is it forced us to do some algebra. That's not a bad thing.
How come you couldn't just integrate u squared plus 1 cubed and think it like
Can.
Just can't do that.
So whenever you're thinking that, Clint, you should be thinking, well, can't I use substitution on it or something? Or think, hey, isn't it the reverse of the chain rule? So if I'm thinking reverse of the chain rule, it's a group to a power. Could I call it u squared plus 1, increase the power to 4, divide by that new power, and divide by the derivative of the inside? Doesn't work. And substitution wouldn't work because of that derivative of the inside being 2u. You'd say, do I see a 2u on the outside? No. I could always multiply by a factor of 2. It's that u that's the problem. So I would have to see in order to use substitution, I'd need to see a u out there. Then I could. But since I don't, I can't. You see the difference in...
For the answer of number 10, the second term, why is 0 not 3?
Oh, because the integral of any exponential function is that exponential function divided by the derivative of its exponent. So you'd say, if you've taken the derivative of e to the 3x, you'd say it's e to the 3x times 3. We just have to undo that when we take the derivative. But now, be careful with that. What if this was e to the 3x squared? You cannot say, well, the integral of e to the 3x squared is e to the 3x squared divided by 6x. That doesn't work. It only works if it's a linear exponent like that. Then you can just say divided by the derivative of whatever's up there. Which is why that one problem that I had 10 to the x squared, I had to use substitution. Okay, so that was 11. Number 12. You see something in this problem. So this is one of the things. We should have been able to handle a problem like this actually in the last section. So using our skills of integration up to this point, do we see where to start in this problem? Go ahead, Susie.
Factor out the denominator.
Not factor.
You replace the whole denominator with u, and take the derivative, and then times the top by 2.
Yes, yes. You say, just notice, sorry, the connection. Now, what led me in the very beginning to think Zach is on the right track? The numerator is of degree 1 less than the denominator. Every single solitary time the numerator and denominator differ by degree 1, automatically I'm thinking in my head, this is a natural log function. This answer is going to have a natural log in it. How does it have a natural log? Every single time, if it's a natural log, the derivative of the denominator must be in the numerator. It must be. So I start looking at that denominator. Derivative of 3x squared, 6x. Derivative of minus 2x, minus 2. 6x minus 2. The numerator, 3x minus 1. So 3x minus 1 is just half of 6x minus. We can make this work. So I will say exactly what Zach said. I'm going to put it in descending order. Let the denominator equal u. So du is equal to 6x minus 2. And I know all of that group is multiplied by dx. be careful that, and I don't know that I'd be mean enough to count off, but please notice this is bad notation. That is bad. That's like saying only the 2 is times dx. So to get the true notation here, you'd say, well, the derivative of u with respect to x is 6x minus 2. So du is the group 6x minus 2 with respect to x. Okay. Technically, you really need a group around that and say that whole group is the derivative with respect to x. Now, and again, I wouldn't count off, but just it's better to have it. Now I can say, well, I know that du is equal to, if I factored this, 2 times the group 3x minus 1 dx. I say, I already see a 3x minus 1 in the numerator. I have my dx here. Now I just need a factor of 2 in order to make all of that du. So I would say, okay, I'm going to multiply by 2 on the inside. If I multiply by 2 on the inside, I have to undo that by multiplying by 1/2 on the outside. So I'll say this problem becomes 1/2 the integral 2 times 3x minus 1 dx. All of that is du. I'll put my 1 on top. You could put the du on top. Now my denominator is u. The integral of 1 over u du, natural log of u. Plus c. So I'll say my final answer is 1/2 natural log of this group, the quadratic, 3x squared minus 2x plus 9. Plus c. Now, what I try to do is I choose the in-class preparation problems is I just go down through your homework assignment and I say, oh, I like that one. Let's choose something similar to it. And I just come up with a problem similar. So when I said that this should be an increasing order of difficulty, I thought so because I thought the problems in the book should be an increasing order of difficulty. I don't think it's really getting harder. I think some of those at the early part of the assignment might be harder than some of the later ones. I think that's going to be the same case with this one. What if I say I want you to integrate the natural log of x, quantity squared, over x with respect to x? Hopefully you're thinking, well, that's kind of a letdown this late in the homework or in the example problems, because the obvious U-substitution is what's inside the group to a power. U equals natural log of x. Derivative of u is just 1 over x dx. I don't like this problem. Because now we see we have a 1 over x dx in there. So all of that is going to become du. The natural log of x squared becomes u squared. So I can say this becomes the integral of u squared du, which gives me u cubed over 3 plus c. Final answer to this problem, u cubed is going to be the natural log of x cubed. Could I do anything with that 3 by bringing it down in front of the logarithmic function, algebraically simplifying?
Get rid of the fraction.
Well, I could get rid of the fraction by calling it 1/3 the group. Oh, so could I do this? Here's my question. Boy, that looks a lot simpler.
I don't think it's right.
It's gonna have to be inside that log.
Exactly. The only time, and this is another little thing I see students make a little careless mistake on, The only rule that you have as far as logarithms is that if the term inside the logarithm is raised to a power, that power can be brought out front. That's not the case here. It's the entire logarithmic function cubed. You can't simplify this. It's left just like you could put 1/3 times the natural log cubed. But our rule is the natural log of x cubed is 3ln x. That's not what we have in this problem. Okay.
I think that's a good one to end on.
After we have 4 to do.
Oh, the next ones are going to all be